Good. So, algorithmic information theory, shortcutted as AIT, as you might have guessed, it formalizes and builds upon one main notion. One central tool, and it's called algorithmic complexity. Now, algorithmic complexity is also known by the name of Kolmogorov complexity or program size complexity. I will prefer to call it algorithmic complexity, but eventually it's quickly going to be shorthanded to complexity. What is it? Algorithmic complexity is a universal quantification of information content in individual digital objects. Okay, there's a lot of words that I should maybe expand on a little bit. Digital objects first. These are objects that can be discretized. They come from a discrete set of objects. So, as opposed to a continuum, like a real number between 0 and 1 wouldn't be a digital object. We can think of a real number as a limiting process of a sequence of 0 and 1s. And in that sense, we could also lift the notion of algorithmic complexity to tackle, what's the complexity of a real number. We will talk about it. But prima facie, we're concerned about discrete objects, those that can be digitalized into, say, computers. Also, it's a quantification, so it really does give a number. It's not like a qualification, or it doesn't just give properties. It gives a number that we intuitively refer to as the information content. And two of the central theme, it's individual as opposed to, so we will contrast it with Shannon's notion of information, in which we view objects as being sampled from a set. And the measure of information is in fact a measure of the set, or the underlying probability distribution. Whereas in the algorithmic setting, we really take the object as is, and we don't impose it to having been sampled from anything else. And it also is universal. This has a precise sense, which is probably hard for me to actually coin in words now, but we will see what is meant by universal. It means that all processes or all ways of characterizing the algorithmic complexity will yield the same value, plus or minus small constants. Small if we compare with the size of the object that's being described. That's very loose for now, but we're obviously going to all make that rigorous at some point. Now, what else can I say? Algorithmic complexity was introduced independently by three people in the mid-60s. So there was Solomonov in 1964, who was puzzled by the problem of induction. He was trying to find a mathematical formalization of induction. There was also Kolmogorov, who, as we shall see, was motivated by a definition of randomness, which is probability free, so which does not involve the theory of probabilities. And this was written in 1965. And finally, Gregory Chaitin, in 66. Yeah, maybe I should say Chaitin was puzzled most by randomness. Kolmogorov was also, he was aware that he was coining a theory of information. Yeah, I mentioned that in the Dropbox I might have a recommended readings. Kolmogorov's paper is worth the read. When we're going to come there, I'm going to put it into the Dropbox and I'm going to raise a flag recommending you if you want to read it. It's a good read. Great. I should add that AIT is still being developed. It's a fairly young theory. The 60s is quite young, and major breakthroughs were made in the 70s. We're going to see that. But even to this day, there's still papers published in AIT, be it in the applications or also in the theory. Great. Here's my, maybe this is where I wanted to get with my comparison with Shannon's theory. I know you don't necessarily know right now Shannon's theory. Well, we're going to do it. I like to think of them as trees. So if we have Shannon has two in there. Information theory. And we compare it with AIT. I guess Shannon information theory could fall in the same bucket with that definition I gave here. It formalizes and builds upon also a central concept, and it's entropy. So the central concept in Shannon theory is entropy. Whereas here is algorithmic complexity. And to define entropy, one needs to, we go in the roots of, well, entropy is defined within probability theory. Okay, so I portray this as being the roots of the tree, if you will. And what are the roots of algorithmic information theory? It's computability theory. Computability theory, by which I mean like Turing's theory of computation. Known as Turing. Maybe you should write it here, Turing's. Excuse me. And so we would say theoretical computer science, if you will. That's going to be a central theme that we're going to investigate. Now, for those who don't know about the history of how Turing came up with his model of computation, because we take it for granted now that we have all those laptops. But the problems that we're trying to solve are in fact very closely connected to the foundations of mathematics. As well, of course, as maybe what we could call actual computers. So it's perhaps a theory which bridges foundations of mathematics with actual devices that we can build and use for universal computation. So I guess what I'm portraying here is that theoretical computer science is in the background of algorithmic information theory, more than Shannon's theory, who gets his roots mainly in probability theory. Now, another team that is in the background, and we're glad to have a philosopher with us. I sent the invitation to the philosophy department, but also philosophy is in the background of AIT, mainly as the idea of Occam's razor, which says that short explanations should be preferred. So Occam's razor was a motivation to formalize algorithmic information theory, or one could also think of it as one of the fruit of the theory. Once the theory has been specified, then we can have concrete measure on how to quantify what we mean by short explanations. As I said, Solomonov was trying to formalize induction, and that's how he got to algorithmic information theory. Okay, eventually we're going to have a tree, so I'm going to put some leaves. That's my tree. Just before, I should say that another way to present AIT, and I think this is what I've done in the description here, is to see it arising as merging together the spirit of information theory that was developed in the 40s by Shannon with Turing's idea of computation. And in the course, we shall thus spend time, I don't like to quantify it as time, but we will review Shannon's information theory first, and then Turing's theory of computability, to eventually come up with algorithmic information theory. I think it's a mistake for me if I jump too fast into, the length of the smallest program, blah, 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 because we sort of forget what problems it was trying to solve. Like, why did people come up with it? And why is it rich, and what can it tackle that Shannon theory cannot tackle? And in what sense does it take Turing's idea and turn it into an actual information theory, instead of just a theory of computation? Good. So yes, coming up there, I'll just, let me erase that. Some of the fruits of Shannon theory are statistics. And they have their counterpart in algorithmic information theory as what I like to call them non-probabilistic statistics. It seems like an oxymoron, non-probabilistic statistics. We're so used to see statistics in the context of guessing what's the parameters of distribution and so on, that it seems like it makes no sense. But this is one of the things that we will cover in the course, non-probabilistic statistics. Also, thermodynamics is close to my heart and is typically understood in the Shannon sense. We need a distribution over microstates. We can make sense of thermodynamics. Let me just call it non-probabilistic thermodynamics. In algorithmic information theory. It also has other fruits, like I mentioned applications to languages. There are cool papers about that hopefully we get a seminar about. Inductive methods, inductive...
You mean like information density in languages, or what? The amount of information conveyed per word or per sentence?
Stuff like that, yeah. Some tools are, of course, just lifted from Shannon information, but some not. Yeah, like you can quantify how close are two languages by just giving them one instance of a book of French, one instance of a book of Portuguese, one instance of a book of English, and you say how would you build the closeness relationship of these languages? Only with single instance information.
The closeness as in like a program to translate the Portuguese book into French, or?
That might be a good measure.
Okay. What about inductive methods? What does that mean?
Yeah, yeah. These are some of the achievements of, well, what Solomonov's paper has holes. Like there's things that don't work. There's diverging series and stuff. But once we have it, you're gonna get into probably the biggest voice of this field is now Marcus Rutte, what he calls universal artificial intelligence. If you have an environment which produces you symbols, and you have to guess what's coming next. How can you formalize? Well, I'm fairly confident that the next symbol will be that symbol. Or, as I like to put it, as an IQ test, you might see, I don't know, that's going to be too easy. Which comes next?
Well, anything, but I mean,
17.
Another prime, so 17.
Yeah. But one can say, why 17? Like, why not 18? Right? There could be a sense in which, why not 18? I just gave you a finite sample. And there is, of course, no ultimate answer. But Solomonov's problem was to try and derive a distribution over that number. The next guessing number, which is high for 17, but is lower for 18. His idea is because if he really is 18 is going to be the next symbol, then somebody's tricking me. He's like complicating the recipe. He's not respecting Ockhams' philosophy in some sense. The shortest explanation for the next number is 17. Mm-hmm. So that's what I mean by inductive methods.
Okay.
Yeah. Thanks for the question.
I also wanted to ask, I missed it, but what did you mean by universal, roughly?
Yeah. All computers will yield the same answer.
Okay. Okay, universal in the Turing style.
In the Turing style, yeah. Universal computation. And yeah, and then we will run into Church-Turing's argument that if there's something better, then the universe is not exactly as we understand it. Because maybe some super Turing computer will be one day discovered. The physics, as they are, it seems like it's not the case, but logically speaking, nothing prevents it. But then we're going to see that.
You mean like a computer that could compute something that isn't computable now?
Exactly.
Yeah, okay, even with infinite time or whatever?
Yeah.
Right.
We will all see those when we're going to Turing's theory of computability. I think, yeah, it's really, it's important to review computability theory to appreciate the ideas behind AIT. Great. And oh yeah, one last fruit. I call it a fruit. Oh no, there's two last fruits. another one that I like is Bennett's idea of logical depth, which captures the non-trivial organization into objects. So it is a more sophisticated notion than just algorithmic complexity. Algorithmic complexity will be very high for very disordered objects. Logical depth is going to be low for very disordered objects. But it's also going to be low for very ordered objects. But it's going to be high for objects that have a short program, but this short program is the fruit of a very lengthy computation. His idea was to assess the complexity in the universe, like us, say. If the physical laws are right, and we indeed come from a Big Bang and very simple equations of motion 14 billion years ago, then that's a short explanation for mammals on planet Earth. But it's an explanation that requires a lengthy computation. So in Bennett's sense of logical depth, we would be logically deep.
Oh, you mean like the program would have to run for a long time?
Correct.
So it's a simple program.
It is
but
a
it's
short
running for
program,
14
but
billion
it
years or
needs a
whatever.
long computation time.
Okay.
It's a more sophisticated idea behind than just a prima facie algorithmic complexity. However, it's definable through the methods of algorithmic complexity. And the last fruit, I call it a fruit again, but that I should write here, is incompleteness. Of mathematics. Hilbert's theory of everything. According to Hilbert, if mathematics is to provide absolute and complete certainty, then there ought to be a formal axiomatic theory for all of mathematics. Namely, a finite set of axioms from which all mathematical truths can be proven by mechanically applying the rules of logic. Okay. At the beginning of the 20th century, there was starting to be a bit of a conflict between mathematicians. Some of them were proposing that proofs should be relying on intuitive arguments. Oh yeah, but that's infinitely small, so let's neglect it. Oh, what do you mean by infinitely small? And some others were questioning this approach and saying, no, mathematics should be formal. There should be very, very rigorous language in which we can establish the validity of a proof. And it's so formal that it could, I use the word mechanically applying the rules of logic. So you can start with a set of axioms and apply a logical rule to, say, one of them and get a new statement. And then combine that with another axiom and some other rules of logic, and eventually you get a non-trivial statement that we could call a theorem. The theorem is the non-trivial statement, and the proof is how did you combine the axioms mechanically with the rules of inference to get to the desired statement. This is the formal approach that Hilbert was describing here. Now, I gotta be clear, Hilbert didn't suggest that it should be the only way of doing mathematics. He was sort of proposing that, yeah, we could have conversations and write English into a mathematical paper, but, in case of disagreements, if we want to remove all sort of subjectivity or all sort of ambiguity in an argument, we can boil it to a rigorous proof. And what he wanted as a theory of everything is that all mathematical truths should be proven from a finite set of axioms. In practice today, the closest we have from such a theory is the set theory of Zermelo-Frankel with the choice axiom, the axiom of choice, together with first order logic. So, I actually even write that down. In practice, today, the closest that we have from such a theory is the Zermelo-Frankel. Zermelo-Frankel set theory. With the axiom of choice. So we typically write ZFC for Zermelo-Frankel and the axiom of choice. That defines the set of axioms. It's a finite set of axioms. I think there's 9 or 8 of them. Can't remember. Together with first order logic.
What's that?
That's the fact that you can quantify over variables, but not over all propositions. So you can say, for all x, x has a successor. X is a variable. It stands for a natural number. And I think second order logic goes a bit wilder. It says like, for all propositions, one can do that, and all logical propositions. Okay, let's start again. So just before the break, I told you about Hilbert's theory of everything. He had a hope that we could coin a formal axiomatic theory, which is a set of axioms that is finite, and a set of rules of inference, logic, which tells us how to combine the axioms into more elaborate formulas. And he was hoping that all mathematical truths could have a corresponding proof. So a proof is start from the axioms, combine them into the statement you want. Now, we arrive at Gödel's incompleteness. In 1931, Gödel puts an end to Hilbert's program. He shows that in all logically consistent formal axiomatic theory, that is strong enough to encapsulate the arithmetics of whole numbers shortcuts. There are true yet unprovable statements. Okay, I repeat, he shows that in all logically consistent formal axiomatic theory that is strong enough to encapsulate the arithmetics of whole numbers, there are true yet unprovable statements. Logically consistent is the property that we cannot show P and not P from the system. Otherwise, we would have proven a contradiction. If you have proven a contradiction, then your formal axiomatic system is basically ruined, because by invoking if P then Q with a false P, then you can prove everything. So it's meaningless. Now, the formal axiomatic theory is strong enough to do 1, 2, 3, 4, 5, the whole numbers with plus and multiplication. Like the arithmetics of the whole numbers. Now, if you have a formal axiomatic system that can do the arithmetics of the whole numbers, and that is logically consistent, then he showed you will have true yet unprovable statement. Unprovable, that doesn't mean unproven. We have plenty of unproven statements. Like the Goldbach conjecture that states that every even number is the sum of two primes. We think it's true, we have verified it very far. 10. 10 is an even number, it's the sum of two primes, 5 plus 5. 12. 12 is apparently the sum of two primes, 7 plus 5. 14, it's apparently the sum of two primes, I guess 7 plus 7. And so on. All even numbers that we have yet come to, no, that's not a sentence, all even numbers that we have verified, they are indeed the sum of two primes, but it has not been shown that for all even numbers it is the sum of two
It
primes.
works only with a number greater than 2, I think, because if you try 2, you can only try to put 1 and 1, but 1 is not prime.
Yeah, thanks. Good point. It must be that. Or 1 is a prime. No, 1 is not a prime. That would be horrible. Yeah. Yeah. So this was just an example of an unproven statement. The idea is that they're unprovable statements, that no proof corresponds to them. Yet they are true. Okay, Berry's paradox. All numbers, all natural numbers, can be described by a statement in English. By at least a statement in English. But what matters is that we have one statement in English. So, for example, 52 can be described by 52. Or this one can be described by 10 to the 10. Or this one can be described by the numbers digits are, and then I start quoting, 6, oops, 6, 3, you've got it, finishes with 7, end quote. We can describe natural numbers like that. Consider B the set of all numbers that can be described by 20 syllables or less. 52 was described with 3 syllables. 10 to the 10 was described with 4 syllables. And this one, the numbers, I need to drop my pen. I need my 2 hands. The numbers digits are 6, 3, 7, 2, 9, 1, 0, 3, 7, 18. This one is described by 18 syllables. And so this guy is in B, this guy is in B, this guy is in B, because we've described them with less than 20 syllables. B being, again, the set of all numbers that can be described by 20 syllables or less. Okay, there's a finite number S of admissible syllables in English. Like if we want to be generous, S is like 200 or something like that. It's much fewer. But after a certain point, like the difference between blah and blah some guy is just going to say, no, you're drunk, they're the same. There's a finite number of syllables that we can distinguish in English. And that number, say it's S. So then, does the cardinality of B is less than S to the power of 20? I've got S choices for my first syllable, S choices for my second syllables, S choices for my third syllable. Oh, well, this will define the 20-syllable words if we're picky. This will be the 19-syllable words, sentences. This will be the 1-syllable words, but whatever. It's smaller than S to the 21. The point is that it's a finite set. Thus, the set of natural numbers which are not in B is not empty. In fact, it's infinite because this set is finite. And in particular, it contains the smallest element. Let's call the smallest element B0. B is the set of numbers that are describable by 20 syllables or less. Its complement is infinite, so it's not empty. It contains the smallest element B0. In other words, B0 is the smallest number that cannot be described by 20 syllables or less. B0 is the smallest number that cannot be described by 20 syllables or less. I've done it in 19 syllables. It has just been described by 19 syllables. One could say that B0 is in B and the B0 is not in B. We have a contradiction. It's in B because of this, the smallest number that cannot be described by 20 syllables or less. I've just done it. And it's not in B by construction. We argued that B is a finite set, the complement is infinite, there's an element which is the smallest, it's B0. So what to think about that? I'm going to be done just after this, but the formalization of algorithmic complexity not only solves the paradox, but it turns it into a proof of incompleteness. Of mathematics. It's going to be Chaitin's incompleteness theorem, which we will see from A to Z. Gödel's construction is a bit tricky. Once we see Gödel's incompleteness, we might say, oh, incompleteness is just a pathology of mathematics. But after we see Chaitin's incompleteness, which is inspired by the Berry paradox, it appears that, okay, it seems to be not just a pathology, it seems to be quite strong in mathematics. Many statements are in fact true but not provable. Well, all right, that's it for today.